Hi, this is 3.3 linear algebra, Cramer's rule. We want to do area, volume, and linear transformations. So we want to use the determine to determine some practical examples, but also learn how to apply Cramer's rule. Cramer's rule essentially is that you take the coefficient matrix that you usually have, and you're going to replace the particular coefficients of a particular variable with the constant terms, and then go ahead and find the determinant, and then go ahead and find the overall determinant of the coefficient matrix and divide the two. So let's just show you how this is done. So if I look at the denominator, I can find the determinant of the coefficient matrix that I do have there. So this is going to be 8 minus 3, which is equal to 5. So that's going to be my denominator there. So if I want to solve for x1, I have the determinant of my coefficient matrix in the denominator, and then the numerator is a modified matrix where I do take the constant terms and put them in for x1. I'm solving for x1, so that's where I do put them in. So then if I solve for this one's going to be 12 minus 7 all over 5, and I'm going to end up with a 1. So x1 is equal to 1. If I do the same thing with x2, I'm going to set this up, and I'm going to put in the 4, 3 here, and then the 6, 7 is going to go where x2 is. Okay? And so then I'm going to divide this by 5. So 28 minus 18 all over 5 would give me a 2. So it's another way to go ahead and solve this system of equations. So x1 is equal to 1 and x2 is equal to 2. You can do this for 3 by 3s as well, but just take whichever variable you're solving for and replace that column with the coefficient, with the constants of the matrix or of the setup that you do have for your 2 equations or 3 equations, whatever it might be. So example 2 has an extra variable in there. It has an s in there. So with that s, what's going to happen is that we're just going to get or find the variables of s for which this system works. So we're going to set this up just like we did the previous one. x1 is equal to, in my numerator, remember I'm going to replace the first set with 3, 2. And then here I'm going to end up with 5 and 5s. This is going to be all over my coefficient matrix 5. This is 3s, and then this is 12 and 5s. So I get my 15s minus 10, and then my 15s squared minus my 60 from each one of these situations. If you notice, I can reduce that down a little bit, so I'll do that. And so I went ahead and solved both of those. Now look at the denominators for x1 and x2. And so if I look at this denominator and this denominator, if I solve both of those, I would get s equals plus or minus 2. Well, that's going to be a situation where the denominator is 0, so we're going to be undefined, and so we're not going to get a unique solution then. And so when s is equal to plus or minus 2, no unique solution. So what you can say is that if s doesn't equal plus or minus 2, then we do have a unique solution, and so then we can describe it. So let's look at theorem number 9 now. Theorem number 9 says that if A is a 2 by 2 matrix, the area of the parallelogram determined by the columns of A is determinant of A. If A is a 3 by 3 matrix, then the volume of the parallelepiped, practice that, parallelepiped, determined by the columns of A is the determinant of A. So if I look at just a regular rectangle, I can do this quite easily if I have A0 and 0D. If I do the determinant of that, I'm going to get AD. And hence that is the area of that rectangle. And if we go over here, I can do the determinant of A0, 0, 0B, 0. My writing isn't so good here. 0, 0, C. And then that would just be ABC. That would be volume. Now sometimes these turn out to be a negative number, so then you just adjust them. This one's the area. So you just take the absolute value of that determinant in order to find the area or the volume, depending upon which one you have. Now, not all shapes are, regular rectangles, parallelepipeds, etc. So what we have to do is still use the determinant of the matrix in order to find it. In class, we'll go ahead and try to prove that with a little diagram thing that I do have. Or you can look at the proof on the next page too and see if you can figure it out. So turning the page, if you look at this, see if you can figure out this proof with just pictures and figure out how to figure out those different areas. We'll do that in class, work with each other, but hopefully you can figure it out before we get to class. So if I look at this example here, example number 3, we want to find the area of the parallelogram with vertices from here. Well, if you notice, none of these include 0, 0. So I'm not going to be able to make the vectors go from 0, 0. In order to use the determinant, I need the vectors at 0, 0. So somehow I got to take one of these points, doesn't matter which one I pick. Okay, let's pick this one. And let's make that one go to 0, 0, and then translate everything else the same way, and then I can use the vectors from that. So I'm going to just subtract the 6, 2 from each one. That will put this point, transform it over to 0, 0. Translate it. So I didn't necessarily pick the most convenient point, but I did get to the origin here on one of the points. So then I can lay out 2 of the vectors, one here and one here, and use those for my area. And they should be the vectors coming from 0, 0. So this one here would be the vector that goes -4, -2, and then this vector would be 0, -2. So I'm going to set that up. -4, -2. Find the determinant with 0, -2. And this would be equal to 8 minus 0, which is equal to 8. And if you notice, this is just the same as a sheared rectangle, which would be right there. So this shearing would be a 4 by 2, so then that would just be that would be 8 anyways. Okay? So that finds the area of the parallelogram translating to the origin, and then we should be okay. For example 4, I have one of the vertices at the origin, and then the other 3 are here. So those already have the situation set up like I want, so I'm just going to go ahead and put these into the matrix to find the determinant, and that would should give me the volume of the parallelepiped that I do want. If you calculate this, you do get -18. But then we need the positive value, so this would be 18 for the volume. Now what happens if we do a transformation of one parallelogram into another using the vectors? What happens to that area? How does it change? Well, the determinant comes into play, but I can go ahead and find the determinant of this one for -7, 0, 1. That would just be 4 minus 0, which would equal to 4. Now we're going to do a transformation, so I can do this one of 2 ways. If I show you the long way, multiply this out. So now the determinant of this matrix, when I did the multiplication, would be to, well, if I calculate this, this is just going to be 12. Well, how does this 4 relate to the 12? How do I get there? Well, I need a 3 in between. How do I get that 3? Well, let's try the determinant of 5, 1, 2, 1. If I got determinant, I got to do brackets, so it's 5 minus 2, which is equal to 3. Oh, there it is. So if I take the determinant of my 2 vectors and then the determinant of the transformational matrix, multiply them, 4 times 3, that's equal to 12. That will give me the area of my transformed parallelogram, which is the 12 here. Okay, so that's just a shortcut way to do that area. All right, here's your practice problems. I hope you enjoy this section and fun with area volume. Take care.